make a little note here, because this will become a very important strategy when we're dealing with the problems we have to do in this unit. Dealing with fractions, this is the title. Dealing with fractions inside fractions. This question has a lot of fractions inside of another fraction. Hello?
Can I get Tobias down to the office for a moment, please?
He'll be right down.
Thank you.
Okay, I'm fine. So dealing with fractions inside of fractions, we have fractions all over inside of this fraction. This is the strategy. I mean, there's more than one strategy that works with these, but this is a strategy we are going to use often. Okay? First, you are going to get a single fraction in both the numerator and denominator. So we have two fractions in our numerator, we have two fractions in our denominator right now. How would I get a single fraction in my numerator and denominator? Right? I'll put in brackets, that's usually your steps for adding fractions. So in our question, how do I add fractions? I need a common denominator. If I want a single fraction in the top, I would need a common denominator multiplying this one by C and C, this one by B and B. On the bottom, this is B over 1. If I want a single fraction on the bottom, I need a common denominator for my fractions on the bottom. Can you see that this one would need to get multiplied by A and A? Now, I will have a single fraction on the top with a common denominator of BC. It will be AB plus C. I will have a single fraction on the bottom with a common denominator of A, and it will be AB plus C. So when dealing with fractions inside of fractions, strategy number one is, can you get a single fraction on the top and a single fraction on the bottom of your big fraction? Because then, step two, you can just divide fractions. As soon as you've got a single fraction divide by another single fraction, your rule for dividing fraction, which is to multiply by the reciprocal, I can now rewrite my top fraction as AB plus C over BC, times by, flip the other one, A over AB plus C. And we're so close, but before I multiply things out, I'm going to look at my factors. AB plus C would get grouped together, that would be a single factor. Do I have any factors that are identical? Yes. AB plus C divided by AB plus C, that would simplify to 1 over 1 and would go away. And so now when I multiply things out, I'm just left with A in my numerator and BC in my denominator. This is the main fraction skill that's going to get used over and over and over again in this unit. Can you write things as a single fraction? Especially when you have fractions inside of fractions. Strategy-wise is pretty straightforward. Get a single fraction in your numerator, get a single fraction in your denominator, multiply by the reciprocal, simplify as best as you can, And now our final answer is a single fraction, and I would say this one looks much simpler than what we started with. So how does this work with trigonometry? Well, if we turn to the next page, we have an important definition here. Can highlight it. Trig identity. A trig identity is a statement that is always true. You know some trig identities already. They were some of our big ideas from chapter 6. For example, tan of theta is equal to sine of theta divided by cos of theta. That's always true. That's a trig identity. You also know that sine squared theta plus cos squared theta is always equal to 1. That would be considered a trig identity because it's an equation or a statement with trig ratios that's always true. And there's hundreds and hundreds of these that exist. So far, we just mentioned 2. Our job is to use some of the things that we already know, right? We already know the definition identities, which are called the reciprocal identities. You know that cosecant theta is 1 over sine theta. Similarly, right above each of these, or beside each of these, the flip is also true. If cosecant is 1 over sine, then sine is 1 over cosecant. If secant is 1 over cos, then cos is 1 over secant. And if cotangent is 1 over tan, then tangent is 1 over cotangent. And these are always true, as long as you're not dividing by 0. Right? And that's why it says in the statement, as long as it's okay to use a number, it'll always be true. Now, we already know that tan is sine over cos. We also know that cotangent is cos over sine. So we can use these identities, and they've rearranged them. So for example, can you see how I could take cosecant equals 1 over sine and rearrange it to look like this? What would I have to do to rearrange it? I have to multiply both sides by sine. Okay? I could take the second one, nope, that didn't work, and rearrange it to look like that. And I could take the third one and rearrange it to look like that. So these become new identities. Now what we're going to do in this unit is we're going to start with these, and if you like, we can also write down this one so far. These definitions, and the big idea that tan is sine over cos, and cotangent is cos over sine, become our tools. And I like to think, like, the questions we're going to solve are called proofs. I like to call them, well, I call them proofs, but I like to look at them more like puzzles. The way that a proof works, and we're going to look at some, we've got a whole sheet, we're going to practice them today. We're going to get started on some very basic proofs. I'm going to hand out a sheet. You will need some loose leaf, so I'll hand out loose leaf as well. Unless you have your own. Okay, perfect. Okay. Take a couple, 2 or 3 pieces of loose leaf, pass it on. I'll do the same thing starting over here. Take 2 or 3 pieces of loose leaf and pass it on. So what I want you to look at after you get your loose leaf, which is coming along, so once you've got a couple sheets, just keep passing it, and they'll meet in the middle, and the person in the middle who has a bunch can just give me what's left. We're going to go to the side that has the word identities written all the way around it. And we're going to start with question number 5, because that's the first question, obviously. And the questions will look like this. It'll say prove, and we have cos, and they use the letter t, times secant of the letter t is equal to 1. And we have some rules. Does everybody have paper now? Almost? So the first thing I'm going to get you to do is I'm going to get you to write down the question. So we always start with the proof question by writing down the question. And we have some basic rules of proofs. Where the equal sign is, draw a line. Because you're going to separate the left side of your original question from the right side of the original question. And it becomes a puzzle in that can you do things to both sides or one side and manipulate it so they end up looking identical. Right now, they don't look identical. I have a 1 on one side. I don't have a 1 on the left side. And what you're allowed to do is you're allowed to use any of the tools that we have on this page to help you manipulate things on the proof. So for example, I can change secant to something. I look at my sheet here. The only thing I can change secant to is 1 over cos. So maybe that would help me. I take this question, I have cos t, and I change secant to 1 over cos t. And I introduce a fraction. And this is why all the fraction work that's going to come into what we did at the beginning comes into these questions. Now, can you see that cos t is technically a fraction too? It's cos t over 1. And how do you multiply fractions? You multiply the tops, you multiply the bottoms. You might also see right away that, oh, this is just going to be cos divided by cos. And these factors are identical, they would cancel out, right? And if they cancel out and become 1 over 1, then this side would just simplify to 1. And we finished the puzzle. The puzzle was, can you get both sides to look identical? The right side started with a 1. We did one small change, a little bit of fraction work, and we got the left side to equal 1. And this is what a proof is. You start with something, and then you make both sides equal the same. There is a little bit of one last thing that you need to do. When you are done, you need to make a statement that you are aware that you proved the left side was equal to the right side. So we say, therefore, the left side, oh, and this is short mathematics for therefore. Even though there's only 3 dots, it means therefore. Therefore, the left side equals the right side. And I also like to add a formal end to a mathematical proof. Many textbooks, when they end a mathematical proof, they, well, I add a little symbol, a little box with little shading, that's my own little touch. But they end with QED. And it's Latin. How's your Latin? Is it good? Pretty good? Right? Any guesses what the Q stands for? Come on, how's your Latin? Latin's not good today? Got rusty. Okay. Quad, probably said terribly. Erat demonstratum. Maybe I said that really bad. But what it means is what was asked for was demonstrated or shown. So you asked me to prove this, I showed you it. So it's a little formal thing that is at the end of mathematical proofs. And then I like to add a little shaded box. You can add your own little symbol at the end. Little smiley face. I don't know. That's just something that I've always done at my end of my proofs. So, let's look at another one. This one, extremely easy proof. This page starts off extremely easy and increases as difficulty as you go down, in so much that number 45 you don't have to do. You can put an X through number 45 because it requires you knowing how to factor differences of cubes, which you don't know yet. Okay, so only 45 will be one that you don't have to do, but all the rest you will be able to do as we go along. So we're going to, you're going to be able to do 6 and 7, but we're going to do 8 together. We're going to do a couple more together. 8 is a little bit trickier. 8 says sine x secant x equals tan x. So, rules for proofs. You've got your left side, you've got your right side. You draw a line separating the left side and the right side. The line is important because in a proof, if you do any math to move something from one side of the equation to the other side of the equation, you lose all marks. Because the only way you can think of it as an equation is if it's true. And you're trying to prove that it's true. You don't know that it's true yet. So all you're allowed to do is work on this side separately and this side separately. So, they're not the same. If we look at what we can do, we can change sine to something, we can change secant to something, we can change tan has two things that it can change to. It can change to 1 over cotangent, or it can change to sine theta over cos theta. But a major strategy that comes up a lot is, if you notice, no matter which trig function you start with, there's always something to change it to either sine or cos. So for example, sine is already sine. Don't even have to change it. Is there something I can change secant to make it either sine or cos? Yes. I could change secant to 1 over cos. Is there something I could change tan to that involves sine over cos? It's sine over cos. So this major strategy often gives us a hint of what we need to do next. If I change everything to sine over cos, on the right side I've got sine over cos. On the left side, I have two fractions that are multiplied by each other. How do you multiply fractions? Multiply the tops, multiply the bottoms. Can you see that if you multiply the tops and multiply the bottoms, you would get sine x over cos x. and our puzzle is done. So sometimes you don't see how you're going to make the sides equal until after you've done some strategies, changed a few things. And we're all done. We'll do 14 as well. Yeah, let's do 14. Prove sine of u over cosecant of u plus cos of u over secant of u equals 1. Draw my line. This is my left side, this is my right side. We need to make them the same. If we think about the strategy from last time, right? Strategy from last time, change to sine and cos. I'm going to even major strategy. I'm going to copy that. I'm going to copy the major strategy over here, because we're going to add a part 2 to the major strategy. Part 1 of the major strategy, change to sine and cos. So I'm going to do that. I can change cosecant to 1 over sine, and secant to 1 over cos. Initially, that doesn't look like I made things simpler. In fact, it makes it look like I made things more complicated. But this is where the thing that we started today's lesson really comes into play. Major strategy, change to sine and cos. I've done that already. Part 2 of the major strategy, write as a single fraction. So this isn't a single fraction. This isn't a single fraction. I have fractions inside of fractions. How do I solve for fractions inside of fractions? This is where at the beginning we said, well, you would need to have one fraction on the top, one fraction on the bottom. Technically, on the top, can you see that that's sine u over 1, and this one's cos u over 1? I technically have a fraction on the top and a fraction on the bottom. So how do you divide by fractions? Multiply by the reciprocal. So my next step, there's my top fraction multiplied by the reciprocal. And over here, multiply by the reciprocal. Now, a couple of logistics things for proofs. Right? We're working vertically. You will notice that, you notice I have a large amount of space in between. Make sure you're using space. Because when you have fractions inside of fractions inside of fractions, and you cramp it too close together, you might forget where one fraction ends and the next one begins. So I have highlighted it here with orange, but I put extra space in between each of my steps just so I don't get confused with what I had before. Some of the other things that I do is when I have fractions inside of fractions, I try to make this fraction line longer and thicker than my other fraction line, because that was my middle of my main fraction. Okay. So now, I've got sine u times sine u. Can you see that if you have sine times sine, you would get sine squared? And if you have cos times cos, you would get cos squared. And it'll all be over 1, so I don't need to show that because the 1 was on the bottom. So we've done the major strategy. We changed to sine and cos, and then we wrote as a single fraction, and this is what we got. Are we exactly the same as the other side yet? What was the other side? It's a 1. We're so close. Anything that you can see that you could do? What? Yeah. So because that's one of our identities, you're allowed to use it. It's on your formula sheet. Anytime you have sine squared theta plus cos squared theta, or whatever variable, in this case sine squared u plus cos squared u, you can make it equal to 1, and now our puzzle is done. We've made the two sides the same, so we can have our final statement. The left side equals the right side. Add a little bit of Latin flair. And we're done our proof. This one was a little bit harder than the last one. We had to do more changes. Okay? Now we've done 5, 8, and 14. So now I want you to start with question 6. It's fairly straightforward. And see how far you get. When you get stuck, ask for problems. If you get stuck and you haven't tried the major strategy, I will tell you, try the major strategy. Change things to sine and cos, write things as a single fraction. This is going to be the most important strategy that you're going to use.